I would compare bikes more to the way of feeling, how they give you hints for the whole thing, and then you just realize then, like to the end, you're like, oh, you're right.
I think I feel spoiled for bikes. Is it like a chair? Is that what I do?
No.
It's
Whoa.
big.
So
Yes,
big,
I
a chair.
don't know.
It's not, no, it's not.
I just used to describe the entire game.
Yeah.
Like, God.
All right. Again, sorry about the packet. I had all these missing pages. So there's a, we're going to cover particle motion, which is on that additional packet that I gave you with the missing pages. So just going over the calendar real quick here. We'll talk about particle motion today. And then we'll do product quotient rule tomorrow. And then we'll be done with the new contents. I think this won't take very long. I think we can maybe even start our quiz review tomorrow. So we'll have tomorrow, I do need to start 3.1, but this won't take long either. We're just going to, this won't be on the quiz. We're just going to have parts of Thursday, all of Friday, and parts of Monday to prepare for your quiz. Your quiz on Tuesday will look a lot like the reviews that we're going to go through. So power rule, particle motion, product, and quotient. Okay. All right, so let's look at page 23. So we're going to talk about a derivative from a motion standpoint. So instantaneous velocity. Velocity is when the object, or the velocity of the object is the derivative of the position function with respect to time. So think of derivative as slope or the rate of change. So if S of t is my position function, meaning that I give it a time value in return, it'll tell me, the function will return me the location or position of the function, then the derivative S prime of t would be the same thing as the velocity function. And think of acceleration as the rate of change of velocity. So it's the derivative of velocity. So therefore it's the second derivative of position. So, and for our course, we're really not going to go beyond the second derivative very much. So it's usually just function, derivative, second derivative. That's usually we're just going to live in these within these three functions for the most part. So acceleration is a derivative of velocity. So you can think of acceleration, a of t, as the first derivative of velocity, but also as the second derivative of position. Okay. The average rate of change is slope between two points. So instantaneous rate of change is asking the exact slope at a specific moment. Average rate of change is the slope of the secant. It's requiring 2 points, and it's just finding the slope between 2 points. Speed is the absolute value of velocity. So if an object has a velocity of negative 30 miles per hour, then the speed is going to be positive 30 miles per hour. It's always going to be the positive version of velocity. Velocity has direction, so if you see positive velocity, that usually means it's going up. Negative velocity means going down. Or if it's the movement is along an x-axis, then positive velocity will be moving right. Negative velocity will be moving left. Okay, displacement versus distance. Displacement is how far you are from where you started, and distance is the total amount you have traveled. So if I travel 10 feet to the right and then turn around and travel 3 feet back, then my distance is 13 feet, but my displacement is only 7 feet. Because if I travel 10 feet to the right and 3 feet back, I'm only 7 feet away from where I started. But think of distance as the total number of steps you actually take. So 10 steps to the right, 3 steps to the left. I still took 13 steps, so my distance is 13 feet. Speed is increasing when velocity and acceleration have the same signs, and speed is decreasing when velocity and acceleration have opposite signs. Particle motion. Particle motion is basically linear motion, meaning that when we talk about particle motion, we're usually talking about an object that's moving along the x-axis, moving along the horizontal line. So typically the notation for velocity and acceleration is still v and a, but typically position is indicated as x sub t, since you're moving along the x-axis. So that's why they indicate that as x sub t. And because we're restricted to only movement along the x-axis, positive velocity would indicate particle moving to the right. Negative velocity would indicate that the particle is moving to the left. And then when velocity is equal to 0, then that indicates that the particle is at rest. The particle is momentarily not moving at that t value. Okay, page 24, whenever you're ready. Okay, let's read through this word problem, and then we're going to answer all these questions based off the scenario. A ball is thrown vertically upward from the edge of a building. And just give them. Let's say this is the edge of the building here, and we're throwing the ball vertically upward, and eventually it's going to hit this peak, and it's going to eventually make its way down, and it's going to eventually hit the ground. Okay. The ball is thrown vertically upward from the edge of a building, and it eventually hits the ground next to the building. If the height of the ball at any given time, this is t is greater than or equal to 0, so we're only considering time to the right of 0. H of t, this is the position function. So there's a lot of different variables that can represent the location of an object. It could be h of t, could be s of t, could be p of t, could be x of t. So whatever they define will be your starting function. So go ahead and put that down here. H of t is equal to negative 16t squared plus 64t plus, sorry, we have a, there's some missing pages from the packet, so we're going to look out for that. Thanks. So let me just talk about what this function does for us. If I give it any t value, let's say t equals 0, or t equals 1, or t equals 2, in return, this h of t is going to tell me how high the ball is off the ground. So it makes sense, right? If I plug 0 in, I'm going to get 80, and 80 is exactly how high the ball is off the ground, because that's where the ball is going to start at the edge of at the top of the building, or 80 feet off the ground. 1 second in, it's going to be some value, some height of the ball above ground. So we sketched a diagram. We're going to need velocity and acceleration. So let's just go ahead and get those out of the way, get all the calculus out of the way. and then we can use it when we need it. So v of t is simply the derivative of height, and all we need to do is to go through power rule to get to the derivative. So negative 16t squared becomes
Negative 32t.
okay plus plus 64, and then 0. Okay, so we can just drop it out. 100 plus 0, we can just ignore it. Okay, so velocity function, let me talk about what this does for us. If I plug in any t value, it'll tell me how fast the ball is moving and in what direction. If you get a positive velocity, that means the object is on the way its way up. If you get a negative velocity, that means it's on its way down. So if I plug in 0, I'm going to get v of 0 is 64 feet per second, and that makes sense because that means at the moment that the ball is being thrown, it is being thrown at a velocity of 64 feet per second. Now, I also want to talk about the fact that I think it makes more sense for us when we think, oh, I plug in the t value and I get a height, or I plug in the t value and I get a velocity. Now, this can go the other way as well. I can identify a specific height and then in turn ask when it's going to hit that height. I can also give it a specific velocity and in turn ask the velocity to tell me the time at which that velocity is hit. So there's two ways that our functions can get. We can either give it time and ask for the height, give it time, ask for the velocity, or you can specify a specific height you're looking for, and in turn figure out how long it takes to get there, or plug in a specific velocity you're looking for, and in turn ask at what moment in time it's going to hit that velocity. So multiple ways. Okay, next up, acceleration. Acceleration is the derivative of velocity, or in other words, the second derivative of position. And what's derivative going to be if I do power rule again?
Just 32.
Just negative 32. Yeah. And the 64 goes away. So this is acceleration due to gravity, negative 32 feet per second. So that's a constant value there. Okay, number 2, how tall is the building? We can relate that to the ball at the beginning of the problem. We know that the ball is located at the top of the building at t equals 0 before the ball is being thrown. So h of 0 is just what? 80 feet. The height of the ball is matching with the height of the building. Okay, when does the ball reach maximum height? So we have to kind of think about this ball's motion here. So when the ball reached, assuming the ball is being thrown straight up in the air, when the ball reaches the maximum heights, what do you know about the velocity? 0. So that is how we can work backwards to figure out, when the ball reaches maximum height. We know that the velocity is going to be 0 based off of the nature of this problem, right? The ball is going to be momentarily not moving before it begins its descent down to the ground. So it says, when does the ball reach maximum height? That is when we know that maximum height is occurring when the velocity is 0. So we can use the velocity function to figure out that moment in time. So we'll plug 0 in for velocity and then solve for t. T equals what? 2 seconds. Yeah. So 2 seconds in, the ball is going to reach its maximum height. And we know it's maximum height because it's going to be stopped for a moment. And it's going to take 2 seconds to get there. So now, well, we know how long it takes for the ball to reach maximum height. What is the maximum height? How can we find that information? The height, yep, because we want to, we have a position function that can indicate the height if we give it a moment in time. So we just plug 2 in. Let me do the math for us since you don't have a calculator. And on the quiz, it'll be easy enough where you won't need a calculator, you won't have a calculator. But let me just do this for us. We're just adding a bunch of these numbers together, and 144 feet. The ball is, after 2 seconds, the ball is going to be 144 feet. That's going to be the maximum height. After 2 seconds, it's going to start falling down.
Couldn't you also just do 80 plus 64? Fun maximum height.
Yeah, that works too. How long does it take to hit the ground? So hitting the ground, that's a location, right? That is when the height is what? Height of the ball is 0. So we're going to use the location of the ball to figure out how long it takes to hit it. So we can replace 0 in for height and then solve for t. Okay, this is a factoring problem here. I'm going to factor -16 out. Multiply to be -5, add to be -4. Solve for t, what do we get? T equals what? 5 and -1. Which one doesn't make sense? -1. So the problem is starting at to the right of 0, so -1 is not going to make sense. The reason why we're getting this as an answer is because if we follow this parabola is going to hit the x-axis at -1, but that doesn't fit the nature of our problem since we're starting in the middle of this parabola here. But numerically, algebraically, it's going to give us x-intercepts for this parabola. So that's why it's giving us that -1. But we just know that it's going to be 5 seconds after the ball is thrown up in the air before it hits the ground. All right, number 6. What is the initial velocity? Initial velocity is when time is what? 0. So we just do v of 0, right? So v of 0 is equal to, yeah, this goes away, right? So 64. Units of measure, feet per second. Okay. Number 7, what's the velocity at 1 second? What's the velocity at 2 seconds? We can just plug 1 and 2 into our velocity functions. Number 8, what is the height at 3 seconds? So just plug 3 into the height function. Again, I'll do the math for us here. Right, it makes sense that we're getting a value lower than 144 because after 2 seconds, the ball is already on its way down. So it's going to be lower than 144 feet. Okay, number 9, what is the speed when it hits the ground? Let's not worry about speed. What's related to speed? Yeah, let's just find the velocity first. So let's find the velocity. Do we know information about how long it takes to hit the ground?
5 seconds.
5 seconds. So let's find the velocity at 5 seconds. So v of 5. And I'll do the math for us. I got -96 feet per second. That is the velocity. But then we can adjust that, right? The speed is what? That's 96, yeah. Speed is just the positive value of velocity. If velocity is negative. If velocity is positive, then your speed will be the same value. Okay, what is the acceleration at 1 second? Yeah, and what's the unit of measure? Feet per second squared. Acceleration in 2 seconds, same, right? That constant is never changing. It doesn't matter what time I put, it's going to be the same constant value. All right, questions so far? All right, put a star next to 11 through 14. These are the ones that are going to give students the most trouble. And I'll talk about why. So it says find the average velocity. Average velocity is defined as the change in position divided by the change in time. And the reason why this is troublesome for many of us is because we see the word velocity and your natural tendency is you want to use velocity function. But your velocity function is going to give you the instantaneous velocity. That's not what we want. We want the average velocity. We just want the change in position over the change in time. So we're going to use the function above it. But we're just going to do h of 2 minus h of 0 over 2 minus 0. So we're not going to touch velocity at all. And that, you can imagine, if we're not careful, that your tendency is you see the word velocity, you want to use velocity, but you're going to use the function above it. So it's going to be h of 2 minus h of 0 over 2 minus 0. I just want to give a, I'll finish this first. So h of 2 minus h of 0, we have that number 144 minus 80 over 2 minus 0, 64 over 2, 32 feet per second. Now, even though we didn't touch velocity function, we're still going to end up with the same units because position is feet, time is seconds, so we still have feet per second. Now, I know that for this problem, I think that the numbers do end up being where if you use the velocity function, you'll get a similar number as well, but the process is what I'm after. Okay. Sometimes students have a little bit of trouble with this in terms of, wait, how come we don't use velocity function if it's average velocity? Maybe an example would be, let's say you're going on a road trip and you knew that it took 300 miles to take that road trip. And you knew that over that distance of time, it took you 5 hours to get there. And so your average speed will just be what? 60 miles per hour. Even though I have no data about how fast the car is driving, I'm just basing off my average speed based off of the total distance traveled and the amount of time, right? And so same thing here, average velocity, we don't need anything from the velocity function. We just need how much distance has been covered and how much time has passed, and that's all you need to find average velocity. Same thing here, average acceleration. If you had to guess, what's the definition for average acceleration? Yeah, change in velocity over the change in time. And again, this is troublesome because you see the word acceleration and then you're natural tendency is you want to use acceleration because you see that word um, in the function. But we're not going to use, we're going to use the function above it, right? Change of velocity over change in time. So we're going to do v of 2 minus v of 1 over 2 minus 1. So 0 minus 32 over 1, negative 32. What's the unit of measure?
Seconds.
Feet per second squared.
But we knew we'd get that right because it was a constant.
Right, yeah, it's a constant. But it's the process I'm looking for here. Is the speed increasing or decreasing? So this goes back to notes that I went over on the first page here. The way we determine increasing and decreasing speed is we compare between velocity and acceleration. If velocity and acceleration have the same signs, then speed is increasing. If one is positive and the other is negative, then speed is decreasing. So we're gonna have to gather some additional data here. So if any time we're asking about speed increasing, you're gonna compare signs between B of 1 and A of 1. So we can say, since V of 1 is 32 and A of 1 is negative 32, what can we conclude? That speed is decreasing. So speed is decreasing. And the reasoning is, I just want you to say, because V of t and A of t have opposite signs. Number 14 is troublesome because 13 and 14 feels very similar, right? The only difference is the word speed versus velocity. But this is not actually talking about velocity. It says, is the velocity increasing or decreasing? This is talking about what? This is talking about the rate of change of velocity, which is what? Yeah, so this is talking about acceleration. So in other words, this is saying, is acceleration positive or negative at t equals 3 seconds? And then we're going to use that data to determine whether velocity is increasing or decreasing. So you can imagine how troublesome this is because you either want to do the same thing that you did with comparing between signs, or you may just rely on velocity if you see the word velocity, but here you're only depending on acceleration. And because acceleration is negative, we know velocity is decreasing. So these four are troublesome because the words can throw off how we interpret it. So average velocity, we don't use velocity. Average acceleration, we don't use acceleration. Speed increasing, you got to compare velocity and acceleration. Velocity increasing, you have to use just acceleration. So it's almost like nothing is what it seems amongst these four options. Yeah. Change of position. So just take the position function and just subtract and divide. Let's look at Let's see here. Okay, let's go back and let's do some more practice with power rule. So page 19. This is the first page of the additional handout that you got. Sometimes you may see other variables, but like they're going to indicate what variable is the independent variable. In this case, for number 11, U is the independent variable. For 13, S is the independent variable. But if you see anything that is not indicated as a variable, like A or B or C, those are just constants. Those are just unknown numbers. So you'll treat A, B, and C like you would if it was like a 5 or 3 or 6. Okay, but try number 7 first, and then have you tried, and we'll go over it. I want to pace you through these problems here. Think of A as just some number that's attached to the variable S cubed. What do you think the derivative of AS cubed would be?
3A.
Yeah.
So 2.
Yeah. We just don't know what that number is, but it's just going to hang out in front just like how other numbers would hang out in front. Okay, 15, I would resolve the parentheses first before I do my derivative. Seventeen and 19, I would split up into individual fractions first.
A little more work for the first one.
Which one?
Oh, wait. That's talking about.
Yeah. Yes. Yeah. So once you distribute through, it's just a nice power rule for each. Nothing more complicated than that. Everybody good up to number 15? 17, once you split up into individual fractions, Sometimes students have a little bit of trouble with how to deal with that 5 below that variable. Where else can we put it so that it doesn't look so strange? 1/5. Yeah, you don't have to do it, but I think a lot of students prefer that 1/5 because then it just looks like a number in front rather than having to stare at a number below. Just looks more familiar that way. Okay, now find the derivative. Power rule should be more straightforward now. Yes, question?
Can you combine that to be 3x squared plus 2?
Sure. Yeah, you can put into common denominator if you like. You don't have to, but you can. Okay, 21. Again, treat A, B, and C like just some unknown number. Pretend A is like 3, pretend B is 5, pretend C is like 6. What's AX squared's derivative? 2AX. What's BX's derivative? Just B, yeah. 5x becomes 5. 8x becomes 8. BX becomes just B. And then the C?
0.
0. Good. Okay, turn to page 30. Remember those problems that I had you guys put a star next to, 11 through 14? This is a way of kind of seeing if this makes sense. Okay, so I have all these data of needed values, and let's see if we can put it all together. So find the average velocity from time 2 to 4. So how do we find average velocity?
Change in position.
Change in position over change in time. Okay, good. And sorry, S is representing position. So S is position, V is velocity, and A is acceleration. Oops, sorry. Sorry, 10 minus 40. I got this. What's the unit of measure? Meters per second. Yeah. Instantaneous velocity at 4. Instant velocity. Now, if you see the word instantaneous velocity, that now he uses a velocity function. So that's just v of 4, which is what? Negative 12. Yes. Is velocity positive or negative at t equals 4? It's just positive, or so this one we can use velocity function, right? This is just what? Negative, yeah. So v of 4 is less than 0, so negative. Now part D is velocity increasing or decreasing. So this is talking about what? Just acceleration, right? So since acceleration at 4 is positive, therefore velocity is increasing. Yeah. Okay, part E is the speed increasing or decreasing at t equals 4. How do we determine increasing, decreasing speed? Good. Compare between velocity and acceleration. Decreasing because different signs. Yeah. If they're both positive, speed is increasing. If they're both negative, also speed increasing. But if one is positive and the other is negative, then speed is going to be decreasing. And then part F, find the average acceleration. How do we do average acceleration? Change in velocity over change in time. We don't touch acceleration. It's just the slope of the function above it. Change of velocity over change in time. So hopefully targeting these specific parts will make us feel more comfortable when we come across these types of problems on the quiz review as well as for the quiz. Okay, I don't know if we finished all of page 15 through 16, but if you can just finish those 2 pages, just more power rule problems, and I'll check that tomorrow. Okay, so page 15, 16 off the main packet.
Yeah, so these 2 pages. Those telling us the easy stuff. I'm like, you're all like.
If you have the island.
No, I don't.
I think this is what I checked yesterday. I said, and then I'll show you 17.
Thank you.
I know she wants made.
Yeah, I mean, here's some 6 days, all like, yes.
We're just gonna work through the packet here and we'll do.
Maybe she's friends with the girl.
We're gonna do product and quotient rule. And then we'll maybe do some of the homework pages. And then we're gonna start quiz review, and quiz review is directly in the packet. So you just follow along with the packet and watch the video. Thank you.
Keep going to 2204.
Yeah, I'll let you go at 10:12.
Low key, no, my mom.
Yeah, she kind of is. Kind of like one day. We want you, Mr. James.
From this.
I've had this year.
Yeah, allegedly.